This is Unit 6, Video 12, and this is the video that we'll end up or finish up with in the chapter. And we've been talking about ideal gases as opposed to real gases, and we showed you an equation that adjusts some of the parameters of pressure and volume for real gases. And now we're going to ask a more qualitative question. What makes gases less ideal? So how can we tell that some gases are more, some gases are less ideal? And here the general statement we'll make is that the intermolecular forces really are the ones to look at. Now we've studied the intermolecular forces in a previous chapter, and we'll actually come back to them in the next chapter and go deeper and recall what they are. They are really important. So intermolecular forces actually apply to real gases, and so they make ideal gases behave like real gases. And if you remember, there are three intermolecular forces. These are the London dispersion forces, and here it says that they depend on size. Remember, London dispersion forces are simply the forces of nonpolar molecules, and because molecules have a big electron cloud, so something like oxygen, and this big electron cloud can get dispersed, can actually go to one side, creating a slightly negative side to the molecule and slightly positive side, and then the same thing happens in the next molecule, and then you get this force that is induced between London dispersion forces. It's just from the movement of electrons. Now, the bigger the molecule, the more electrons it has, and the stronger these dispersion forces are. That's why it says depends on size. Dipole-dipole forces are just from polarity. If the molecule is polar, it'll have dipole-dipole forces, and the more polar the molecule is, the bigger the difference between the positive and the negative side, the stronger this force will become. And then we had hydrogen bonding. Hydrogen bonding includes three cases. Remember, it's hydrogen attached directly to one of the three most electronegative elements: fluorine, oxygen, and nitrogen. And remember, what happened is these are so electronegative that they're essentially able to pull the electrons very, very much off of the hydrogen, exposing the nucleus. Being that hydrogen has only one electron, that electron is taken away, the nucleus, positive nucleus, is exposed. Hydrogen is, a little embarrassed about this, but it is what it is, and that creates a very strong positive side, which allows it to attract the negative side of a neighboring molecule. So, an example of this would be hydrogen. If you compare hydrogen, just H2, diatomic hydrogen, to SO2, sulfur dioxide. Both of these are gases, but if you start taking pressures under different conditions, you'll see that hydrogen can be much more easily explained by PV/T, and SO2 begins to deviate from that. You'd have to apply the real gas law equation. Its pressure, for example, doesn't line up with PV/T as well as hydrogen does. And if you analyze the forces of hydrogen, first of all, it's nonpolar. Hydrogen is simply a diatomic molecule that looks like this, and hydrogen is extremely tiny, so it's got dispersion forces. All it has is LD, but those dispersion forces are really small, meaning that it's going to behave like a gas, much less like a liquid. Remember that these IMFs, if they're present, they make the gas behave as a liquid. Whereas if you analyze SO2, SO2 is actually polar. The reason why it's polar is if you draw its structure looks like this, and if you recall, this allows us to have a bent geometry. So because it's bent, because of that lone pair, this guy becomes polar. Now, because SO2 is polar, it has dipole-dipole forces, which cause attractive forces between the molecules. Not only that, it is quite a bit bigger than hydrogen, because you've got sulfur, which comes from a lower period on the periodic table, so it's bigger to begin with, 32 electrons on sulfur, and so it's a bigger molecule, so its dispersion forces are greater as well. Not only does it have dipole-dipole, so SO2 actually experimentally will show deviations from ideal behavior, and that's the idea. Alright, so this really is a focus on intermolecular forces, and we'll pick this concept up in the next chapter. So, taking a look at this table that we've seen earlier, these are the constants for real gases. If you take a look at the table, what you'll see is that the constants are smallest for helium, whether you take the constant A or the constant B, and they're biggest for, in this case, CCl4. Now, CCl4 is actually, if we ignore CCl4 is just a really big molecule. So its dispersion forces cause it to have very strong London dispersion attractions. But if we just so it's technically a liquid. So here, this is technically a liquid, and water is also technically a liquid, even though we can look at it in a gaseous form. That's why these are so much different. So if you take a look, for example, at nitrogen and oxygen, compare these here: nitrogen, oxygen, and then helium. These are definite gases, and so is CO2. CO2 is also a gas. You'll see that the bigger the molecule, all these are nonpolar, by the way. So nonpolar, nonpolar, nonpolar. The reason why CO2 is nonpolar is because it has, if you recall, 2 double bonds. Looks like this. And so, being the biggest, CO2 is definitely the biggest of those three. It has the largest constants. Same thing here. You can also see the difference with nitrogen and oxygen. Nitrogen actually has a bigger constant than does oxygen. And if you remember on the periodic table, nitrogen is to the left of oxygen. So you have nitrogen here, then you got oxygen here. So going right, remember we get smaller in size. So in fact, you can see this difference. You see, because nitrogen is bigger than oxygen, you see nitrogen has stronger dispersion forces, so it has a higher constant. Same thing here. Nitrogen has a higher constant. So this is definitely related to intermolecular forces. Water, look how big the number is for water compared to the others. And that's because water has hydrogen bonding. It is a tiny molecule, so its dispersion forces are weak, but the hydrogen bonding makes up for that, more than makes up for that. And then this guy just has very strong dispersion forces, being such a big molecule. So there it is. You can actually analyze these constants and see in these constants this idea of intermolecular forces. So let's wrap up with a little example problem. And this example problem says rate these gases from most to least ideal in behavior. So we want the most ideal and then the least ideal gas. Now between these two, or between these three, what we see is this one is nonpolar. Fluorine is just diatomic fluorine. This one's polar, because you have a difference between oxygen and carbon in carbon monoxide. And this one here has hydrogen bonding. So the one that has hydrogen bonding has the strongest intermolecular forces, so it will be the least ideal, the more real. So we want from most to least ideal. So least ideal would be NH3. NH3 would be very, very last. And the most ideal should be fluorine then, partly because fluorine is the smallest. The atoms are smaller because fluorine, remember on the periodic table, is all the way on the right of the second period, and then carbon and oxygen are in here. So fluorine would be the most ideal, and so then carbon monoxide would be somewhere in the middle. So we can actually predict just from intermolecular forces which gas will be more ideal, which gas will be less ideal. So that's how important intermolecular forces are. So we will come back to them, and we will talk a lot about them in the next chapter when we talk about liquids and solids. And for now, we leave you for this video.